Today we're going to look at exponentials and logarithms. We're looking at lesson 6, modelling curves. And we're going to take two types of curves and see if they are suitable to fit the data required. Often when you do experiments and you get a series of data, you'll get your x values and your y values, your independent and your dependent variables, and then you'll want to see if you can form a relationship between the two. Is there a relationship? Because if you can work out a relationship, you can make predictions. And so what we've got to do is we take these two, and then what we've got to say is, well, how do I actually find the constants for the relationships? And the way you do that is you transform them into straight lines first, and from that you can find the constants, and then you can see two things. One, are they a suitable relationship? Do they form a straight line? And if they do, you can then work out what the constants are, and then you can actually get the true model equation. So that's what we're going to look at. We're going to look at two things. First one, we look at equations that they consider to be in the relationship y equals ka to the x. And then we're going to look at those ones that are exponential ones, where they think, gosh, it looks like an exponential. And that is in the form y equals kx to the a. Now, as I said, straight lines are really powerful. We've got our plumber here. And we know that if he gave us a series of data, we'd be able to plot a straight line. And from that, we'd be able to work out how much he calls his call-out charge, because that'd be the y-intercept, and we'd better work out his hourly rate, because rate, remember, is gradient, by looking at the gradient, and that would give us our hourly rate. So getting a straight line is a really powerful thing to do. So I'm going to use the examples in the book. First one, we're looking at y equals kx to the n, and in the example here we've got a water pipe, and we want to see what the pressure is, the rate of flow per second, depending on the size of the diameter. And so what happens, they get a table 13.2, a series of data here, and they're thinking, they suspect that there is a relationship there. Perhaps they've modelled it and it looks like a relationship, and they think, maybe it's in the relationship r equals kd to the n. So the question then says, well, let's look at the graph of log d against log r. And now, why are they asking us that? Well, let's see why. First of all, it's log base 10. So I'm not going to put the base 10 there. Let's assume it's all log base 10. Log both sides, and then use the rules of logs that you know, a bit like the indices rules. And that can be changed to plus, and then that n drops down. And if I swap these two things around, you can see I get log r equals n log d plus log k. And hopefully you'll see that's very close to the relationship y equals mx plus c. And that's really powerful, because if I were to graph these two logs and they form a straight line, then that is a suitable model. So really, the n and the log k are really important once I deduce that log r and log d form a straight line. So therefore I need a new table. And in this, instead of having the d values of 1, 2, 3, 5, and 10, I'm actually in the log d of those. And instead of r values being 0.02, etc., I'm doing the log of those. And here I get this table here. Now, if, when we graph this out, it looks like a straight line, then this is a suitable relationship to use. And that's the power of this. Yes, it is a straight line. Now, it's not always going to be perfect. There could be slight inaccuracies here in the way you've measured the temperatures and your time logs or whatever like that. So it won't always be a perfectly straight line, but don't worry about that. So now, yes, there is a suitable relationship. I need to find the constants. So I need to find n, and I need to find log k, sorry. Now you can see log k here is our y-intercept. So this is our y-intercept. Now remember, that isn't our value of k, that is what log k equals. So you need to remember that, log k equals that. So I need to do 10 to the power of minus 1.7 to actually find what k equals, 0.02. So that's our constant. Now let's look at the n value. And in log form, that represents the gradient. So take two values, subtract the y's over the subtraction of the x's, and you get its gradient form. So r equals 0.02 d to the 4. And as we said, because there's a straight line there, that is then a suitable relationship to use. What about exponential functions? Very, very similar, but this time is slightly different because our x value, in this case t, is the power, and so that has a slightly different play to it all. So here's a temperature theta of coffee, after so many minutes of it being brewed. And firstly, they say plot theta against t. You do that in order to determine what type of relationship you think it may be. And when you do that, it looks like it's an exponential. And therefore, you say, well, if it is, then is the form theta equals ka to the t a suitable form to use? So if it is, then if we did the log graph of it all and we get a straight line, then we know, yeah, great, we've got it. So let's do the same as we did previously. But this time, remember, exponentials, so we're looking at the natural base here. So it's ln theta. So ln on both sides divides, t drops down. But there's something you need to really be aware of here. Slightly different here, our x value is t. And that's kind of really important here because our t values here aren't altered then. They stay in the form they were given, 2 minutes, 4 minutes, 6 minutes, etc. But our y value is the natural log of theta. So that is the one that changes. Now, if there's a straight line here, then this is a suitable model to use. And yes, it is. There is a nice straight line here. So therefore, let's work out the constants. I can do either way, but I'm going to find the gradient first. So I'm going to take two values, subtract the y's over the subtraction of the x's, and I come out with the gradient. But this is, remember, this is the coefficient of t here is ln a. So the gradient is ln a, not a. So I need to find a, so I do the exponential on both sides, and I come out with 0.93. Now, as I said, it's not always going to be exactly that. I think the book has it slightly differently, because if you were to use slightly different values, it may come out slightly differently. So be careful with the level of accuracy. You don't have to be that accurate. Remember, this is modelling, experimental approximation. So I've got my a value. Now let's work out the y-intercept. It's not clear here. The data doesn't tell you what it is. Okay, but we can graph it and then look for it. We can use our graphic calculator and do a tracer back. We can even look at the gradient movement up, maybe. But let's assume in this case it's 4.55. Now again, remember, that's what ln k equals. So therefore I need to do the exponential on both sides, and I get e to the power of 4.55, which comes as 94.6. So I know, therefore, my k value is 94.6. Equation equals theta equals 94.6 times 0.93 to the power of t. I hope this has been helpful for you. I'd like to now try exercise 13.5. Have fun. Talk to you later.